All right, so with step 4F here, you see we're going to need to calculate the acceleration and the change in velocity. Okay, so again, we have our bits of code here that we can copy and paste. Let's go ahead and do that. What do we need to know about the acceleration, Chris?
Right, so if you paste that in, go ahead and paste it below what we just did. So you notice that there's these comments on the end. And what do we know about these slashes? What's the rule whenever you see these slashes?
Whenever you see the slash, and sometimes that in other languages can be the semicolon or a % sign or something like that. But that tells you that you're commenting something and that the computer is not reading it. That's basically there for you to figure out what your code means. What does it do? So it's a note to self, I think.
Yes, so what is this note telling us?
Let's see here. Our AX times our DT is what is going to be our delta VX. All right, so what was delta Vx again? That was our change in velocity in the x direction.
Yeah, just for this time step, just for this sort of moment in time that we're simulating, the velocity is going to change by some amount. So this little comment here, it's basically reminding you that this thing here, all this is the acceleration times the time. And I could have put in a new variable, ax equals fx divided by the mass times dt. But then we'd have 4 lines of code to add instead of 2, and I just wanted to keep it as simple as possible. So I just went ahead and added these comments here just to remind you that this is acceleration times the time. And you guys have seen this in some of the other coding activities. There's places where you have ax times the time. And by the way, this dt is delta t, so this is some time interval, so it's like 0.1 seconds or something like that.
Okay. And that fx over the mass comes from Newton's law, F equals ma, right?
Exactly.
So we're substituting a for F over m in this case. Okay. So we've added some acceleration. Let's see what else we have going on here.
See, now I think we're ready for some fun. So
okay.
Now I think we can go ahead and
should we
set
push
it loose
play
and see what happens. Here
okay.
we go. Yay! That's pretty cool.
All right. So no more straight lines.
That's great. So this is kind of what we're hoping to do, right?
I think this looks pretty good.
Yeah, you guys can play around with it as much as you want. Like, use the mouse or touch and drag and things like that.
Right, so we have a nice elliptical orbit here.
Mm-hmm. Now what happened there? Why didn't we make an ellipse there?
It didn't come close enough. Didn't give it enough velocity, enough force.
Well, it seemed to me like we gave it too much velocity, right?
Too much velocity and the distance. So
yeah.
we could give it a little bit of velocity, and it's still pretty far away over here. Let's see what happens this time.
Right. So it's kind of like a Pluto orbit, right? Or some...
Oh, it's coming back around.
Some outer planet there.
Okay.
Would you say that it's tracing the same path over and over again?
It looks to be a closed orbit to me.
Yeah. Yeah, I should probably try to give more dots to it. But yeah, so it's working. The code's working. I think this is what we're trying to do. It worked out. I think this is, I think we give ourselves a high five that we finally get this thing to work.
All right.
There you go. So the fun part is that in a minute, what we can do is we can change the strength of gravity and how it depends on distance. And so in a minute, we'll get a chance to do that. The thing we can do before that point is we can actually modify this draw blob function.
Okay, right here?
Yeah, to show the force vector.
All right. So we have our x, our y. So we have our positions, we have our velocities, and then we have our forces for each component, x and y. So let's find our draw blob. I think it's down at the bottom. There we go. All right, so you notice that for draw blob here we have our position, we have our velocities, and our forces have been set to 0. So let's go ahead and change that. We want F in the X direction, and we want F in the Y direction. Okay, what's going to happen now?
So now there should be a blue arrow.
Okay, so this blue arrow is giving you the magnitude of the force. And it's calculating that from our X and Y coordinates.
Yeah, do you want to drag the screen a little bit more towards the left so we can talk about it? Let's just let it keep doing that.
Okay.
If we can. So what do you notice about the length of that vector as it orbits?
Well, it's changing. So when it gets closer, when it gets closer to the sun, you can see it's larger, and when it's farther from the sun, you can notice that the sun has less of an effect on our planet.
And that, yeah, and it's also always pointing towards the sun, right?
Right. Remember that the force of gravity is never going to repel, it will always attract.
That's right. So yeah, it looks like it's working. Now for those of you at home, if you think it would be more interesting to do, a black hole and like a star orbiting a black hole, something like that, all this math, this whole program is all applicable to that. So if you go into the guts of this thing and you change this yellow sun to black, like you can do that. Look, that's totally fine. That's one of the fun parts about this activity is that it's relevant to so many different systems, like we were talking about earlier.
Boom. Too close.
Yeah, too close. So if you get too close, then the program might not be able to be very accurate. So that's why there's a little warning that pops up if you do that.
Let's try again here. Oh, all right. Let's come over here.
But yeah, there's actual comets that make close encounters with the sun that do almost exactly that same thing. So this could be a comet orbiting the sun. It could be a planet orbiting the sun. It could be a white dwarf orbiting a black hole. It could be a neutron star orbiting a black hole. It could be satellite orbiting the Earth. The list goes on. There's so many different applications of this same kind of a thing.
All right, so we've completed through step 6, and we have our optional step 7 here.
This one's actually really easy to do, so
okay.
We should go ahead and do that. So we can either copy this code in, or we can just modify our existing code. The main difference here is that right now for draw sun we have zeros. We have zeros on the end here. But what we can do is we can draw the force vectors, the force that the planet exerts on the sun. And so if we just replace that, see what happens. And we're taking the forces that we calculated up here, and all we're doing is multiplying it by a minus sign.
All right, so let's see what happens.
There you go. So the planet is applying a force onto the sun. Now we're still not allowing the sun to move, but it's just kind of fun to see how the planet's applying a force to the sun's applying a force to the planet. The force is actually the same strength. It's just that it's in opposite directions.
Right. And that's a pretty cool concept, that the force is the same magnitude for both objects.
It's almost as if they're equal and opposite force.
It's almost like that. I feel like Newton had something to say about that.
Yeah, so that's all that means, is that they're opposites, they have a minus sign here, and they're equal so that the strengths are still the same. So this is just a fun way of kind of illustrating it. I figured it was